In this session, I would like to demonstrate another mass balance problem involving a chemical reaction with recycling. The previous problem involving a chemical reaction with recycle, we have used a component separator, but in this particular case, we are going to use a flash column to effect the change or the separation. The product is going to be recovered from a flash column instead of a component separator. So you can see it's an ammonia reactor loop. So nitrogen, hydrogen, argon, methane, argon and of course argon and methane are inerts entering at this temperature and pressure. So the reactor, which is considered to be modeled by an equilibrium reactor, R equal in Aspen, is operating at a high pressure of 200 atmospheres and 500 degrees centigrade. So the vapor and product streams, because the equilibrium reactor will be having both of them, are mixed and cooled to minus 28 degrees Fahrenheit and then admitted into a flash column. So you know the conditions, temperature and pressure of the flash column. So the product is withdrawn, the liquid product is withdrawn, and the vapor after partially purging is sent back in the form of a compressor, in the form of a recycle after compressing it to the required pressure. So one small issue, especially when the pressure is quite high, beyond 15-20 bar, then you need to be careful while utilizing or while selecting an appropriate property package. So probably, if time permits, I'll try to address this issue in one of the theoretical lectures. But let us see how to handle this simulation using Aspen. So the various components that we are trying to handle in this case are nitrogen, hydrogen, methane and argon. And of course, the reaction product is ammonia. So these are all the components we are going to handle. So go to the next input step, wherein you are required to choose a property method. So as far as property methods are concerned involving high pressures, as I said, you need to be slightly more careful. So the mixing rules will come into picture. So probably let me check up. Solve a model with the mixing rule Fioran and Weider. Right? So I'm selecting this. Generally, you are supposed to take some model representing the mixing rule for estimating properties, usually at high pressure. So let me take this. So go to the next step. Okay. Go to simulation environment. Now develop your flow sheet. So as you can see, nitrogen, hydrogen, methane and argon are going to enter into a reactor. So equilibrium reactor model. So let me select that. Then the vapor product and liquid product are going to be mixed. This product is then cooled to some temperature. So let us use a heater model without going into the details of design in order to mass balance. Then after this, we are going to use a flash column to separate out the product that got formed, and the unconscious process, after purging some quantity, we are sending it back in the form of a recycle. So I have a splitter, and then before putting again into the reactor, the fresh feed is going to be mixed with the recycle stream after compressing it to the required pressure of 200 bar. So because the fresh feed is mixed with the recycle stream, I also need a mixer here. So these are all the models that we need in this problem. Let me slightly adjust them. Now let us connect the inputs and output streams. This is the fresh feed stream. The combined feed is entering into the reactor. So the vapor product, reactor, and the liquid product from the reactor are mixed together, and the mixed product is reduced to minus 28 degrees Fahrenheit and then sent into a flash column. The liquid is taken, withdrawn as a product, and the vapor product sent into a splitter. A small fraction is purged, and the remaining is sent back as a recycle after compression. It should not be a problem. Let us go ahead with defining this problem. So 77 degrees Fahrenheit under 200 atmospheres. So you are given the flow rates in terms of LV moles. So let me define this data and change it to engineering unit systems. 77 degrees Fahrenheit, 200 atmospheres. We know the mole flows of various components. 24, 74.3. Nitrogen is 24. Hydrogen is 74.3. And I think it's 0.6 and 1.1. So 100 lb moles per hour of the feed, fresh feed. Then go to the next input. So we are asked to define the equilibrium reactor model. So the reactor is operating at 200 atmospheres and 500 degrees centigrade. So specify that. Fahrenheit, 500 degrees centigrade, 100 atmospheres, or you can say even 0, because the pressure drop when you neglect input pressure becomes the exact pressure, or you can say 200 atmospheres. And you need to define the stoichiometry of equilibrium reactor model. Nitrogen 1, hydrogen 3, and the product stoichiometric coefficient of 2. So this is allowed to reach equilibrium. In practice, this may not be. We may not be in a position to provide enough residence time in the reactor, because as equilibrium, the driving force becomes infinitesimal and you require infinite sized reactors. So normally when you go into practice, we may be allowing 80% of the equilibrium conversion or 90% of the equilibrium conversion to attain by reactors. So usually it may not be possible to reach equilibrium conditions in an operating plant. That's a different story. So we have defined the reaction. Go to the next input. So this is with respect to the heater. Now it is being cooled. The outlet from the reactor is cooled to minus 28 degrees Fahrenheit. Let us say with a 0 pressure drop. So next. Now these are the conditions of the flash column. It is operating at minus 28 degrees Fahrenheit, 1000 psi. 28 and 2000 psi. Right. So you can see some more information is required. Split fraction, splitter, what is the purge? Purge is S9. We are sending out 4%, which is also specified in the problem. So S9 is 0.04, the compressor. Entropy, the discharge pressure is again 200 atmospheres. Input is complete. See, why is it required to compress it back to 200? You have seen already the feed is at 200. If this stream is not compressed to 200 but at a lower pressure, the pressures. So at least you need to compress it back to the same feed pressure or the reactor pressure. There were some warnings, you can check it up. So again, why there is Weierstrass method, why all these loops, all these blocks are iteratively solved for about 21 times. This is because of the recycling. Now, I think you can see from the control panel, the computational order is B3, B4, B5, B6, B7, B1, B2. So again, what is the test stream? The simulator is able to identify. So S5 is considered to be the test stream, and the moment you take S5 as the test stream, this is the computational sequence. So let us check it out. Where is S5? So we are taking this as the test stream. So we will be starting with guessing for the stream. We will be able to solve this hater model to calculate S6. Known S6 and the operating conditions of this block, we should be able to calculate, solving this model, we should be able to calculate S7 and S8, then solve B5, then solve B6, then solve B7, then solve B1, then solve B2. The moment you solve B2, we started with an approximation for S5 set of values for this initial approximation for this tree. Compare these two successive values, and if all the variables come to a convergent solution, then the iterative process stops. Otherwise, we'll be starting with fresh guesses for the tear stream, and once again, the next iteration proceeds. So there are ways. For example, the new set of values that you got for this stream will be replacing the previous guesses. In such a case, the process is known as successive substitution. But normally, successive substitution is slow in convergence. So we'll be using a model, Weierstrass. This is nothing but convergence promotion technique. So we'll be accelerating the conversion using technique. So if you are interested, you can go out into the literature and see what it is. But how is it able to find out S5 as the test stream? Why not S11? Why not S10? Why not S8? Why not S2? Why not S6? So there are some algorithms by which these test streams can be found. So Aspen itself might be using one of those algorithms to identify the test stream. Unless and otherwise you decide on this test stream, you will not be able to come up with this computational order. For example, in this case, if I happen to select S11 as the test stream, the computational sequence will be B7, B1, B2, B3, B4, B5, B6, and then by the time you come here, you will be able to get an updated value for this stream. So check for convergence and proceed with one more iteration until you reach the convergence. So anyway, you can now check up for your results. We were able to solve the problem. Let's see what are the results of your flash column. See, for example, out of 47 moles of ammonia entering into the column, based on the conditions of temperature and pressure at which this flash column is operating, we were able to recover 39 or roughly about 40 kilomoles. Still 7 kilomoles are finding its place in the recycle. Similarly, you can see, you can probably check up what will happen if you try to change the temperature and pressure so that the recovery of methane in the product stream will be higher. So the options are, you can increase the pressure, you can increase the, see this, and another option is, if you increase the pressure, the recovery may be more, but the purity of this methane may reduce. I'll try to slightly run this problem with some other pressure. Just have a look at some of these values, or I'll probably put it into some kind of a. See, these are the results when we operated the flash column at around minus 28 degrees Fahrenheit and 2000 psi. We were able to get the product ammonia with this purity, able to recover 40 kilomoles per hour, LB moles per hour out of 47, 40 by 47 fraction recovery. The more the recovery, that would be better, because this product going into the recycle will not serve any purpose, only to increase the size of all the equipment. In the reactor, you can see only the vapor product is available at this flows. Out of 54 moles of nitrogen that is entering, 34 moles are coming out. So the conversion with respect to nitrogen, 54 minus 34 by 54, roughly 20 by 54. So you can check it out. So what will happen if you change the temperature and pressure at which this reactor is going to operate? Maybe if you are interested, you can perform some sensitivity analysis, seeing the effect of temperature and pressure on the conversion and varying the temperature and pressure in the flash column. You can do such analysis because you are already equipped with handling both sensitivity as well as design spec. I will leave it to you. But I would like to run this problem by increasing this pressure to some other value, slightly increased to 2500 psi. Let me run this problem again. I did not copy the previous set of results. So this was the recovery and this was the purity at 2000 psi. Now what would happen if I increase the pressure to 2500 psi? Right? Summary. Let us look at the results of your flash so that things are easy. So do you see any change? The purity, what happened to the purity? Earlier I think it was, let me also copy this. Just for the sake of comparison, I am putting it side by side. So these are the results of the flash column operating at minus 28 degrees Fahrenheit and 2000 psi. Under these conditions, we got a purity of 78% in the liquid product with respect to oxygen. This is the product we are interested in. But what happened when we increased the pressure from 2000 to 2500 psi? Now the purity of the product has come down from 78 to 74. And what happened to the recovery? Of course, you need to calculate the recovery. There may not be much of a change. So in the same way, you can also see the effect of changing the temperature and pressure at which the reactor is operating in order to promote the conversion. So you will be able to do those calculations using sensitivity. So with these remarks, I would like to close down my session.